Okay. So, in today's class we are going to complete our discussion on normal forms. So, let me introduce what are called multi-valued dependencies and then define the fourth normal form. Look at this example relation, which is really interesting. For some reason I have combined students with courses and their courses and their friends, not courses friends, students with their friends and their courses. For some reason, let us say we have deliberately made up this relation. So, the idea here is that the student enrolls for several courses and obviously he or she will have several friends. So, we want to keep track of this information. So, the friend is represented by the friend email address. Okay. Now, obviously the key for this relation is all the three attributes together. Okay. And so, do there exist any non-trivial functional dependencies here? Does roll number determine anything, course or friend? In general not, because I have multiple courses I am doing and again I have multiple friends and all that. So, likewise you can see that course does not determine anything and friend email address also does not determine anything. So, there are no functional dependencies among the three attributes that we have here. And since there are no non-trivial functional dependencies, the relation actually is in Boyce-Codd normal form, right? It is in Boyce-Codd normal. The highest normal form that we know of right now is the Boyce-Codd normal form, and it is in Boyce-Codd normal form because there are no so what the Boyce-Codd normal form says is that for every non-trivial functional dependency X determines A, X should be a super key. Now, there are no non-trivial functional dependencies at all here. So, but now look at the interesting consequences of having to store data in this particular relation scheme. Supposing I have details about a particular student whose roll number is given here and he is doing two courses. Let us say he has a couple of friends, Radha and Shyam. Now, I would not be I should not be just storing these two tuples, that this student, it is all the same student anyway, this student with this course 370 and Shyam and 376 with Radha. So, this would imply that my doing this course has something to do with having a friend by name Shyam, or doing this course has something to do with having a friend called Radha. So, we very well know that these two things are independent things. So, if we do not want to convey any such associations, then it is imperative for us to kind of store, if at all, if I have these two tuples, I should actually swap these two values and store the other two tuples also. Otherwise, I would be conveying some kind of an association between the courses and the friends, which is not really there in reality. So, in general you can see that if I have registered for some half a dozen courses and I have half a dozen friends or more friends, probably 10, popular guy. So, then we will be having some 60 tuples here. A huge amount of data redundancy exists here. The relation has huge amount of data redundancy, but all the machinery that we have set up so far is not able to detect that because there is no functional dependencies. Okay. So, this is the kind of situation that is detected by what are called multi-valued dependencies. So, before we formally define them, let me show some more examples. Actually, I will define them informally like this now, that whenever we have two tuples of this kind, we are forced to have the other two tuples where I swap the values of these third column values. By swapping I mean, so I put delete Shyam here and put Radha, and then that tuple should be there. So, 370 Radha is there. In a similar way, I take out Radha here and then put Shyam here, and then 376 Shyam should be there. That is what I am swapping basically. So, in this kind of peculiar situation, and you very well, I mean, you can kind of guess that this kind of situation has come up because these are two independent multi-valued attributes of the student, and we have sought to put them together into one relation. And so, this kind of messy situation has arisen. So, for notation we will say that multi-valued dependency roll number multi-determines course exists. Roll number multi-determines course exists, and so by symmetry we can also see that roll number multi-determines friend email address also kind of holds. I will tell you the formal definition in a short while. Okay. Now, in this let us look at this slightly different relation scheme, student course grade. I have roll number course number, but then grade. Actually the grade depends on roll number and course number, right. So, even though roll number the course number is in fact a multi-valued attribute of roll number, just because having a multi-valued attribute does not mean that we will have a multi-valued dependency. I want to illustrate that. So, in this case let us say same student. So, if you have 370 and grade A, 376 and grade B, that does not if these two things appear, it does not mean that these other swapped tuples should appear in the thing, because they are actually dependent, right. The grade is in fact dependent on roll number, course number. So, it is not the single multi-valued attribute that is causing trouble, it is the existence of two independent multi-valued attributes being put together into a relation, that is what is causing trouble. So, MVDs arise when two or more unrelated multi-valued attributes of an entity are being represented in a particular relation. Now, here is another example. In this case roll number, course number, advisor. Okay. Now, suppose we again consider these two cases. If you swap the third column values here, it results in the same set of tuples anyway. Okay. So, swapping either of them, course number or this one, will result in the same number, same existing rows only. So, it can, if the definition is asking for swapped rows should exist, in fact they do exist. So, in some sense, so in this case it actually holds, but then it's but then this kind of situation would have been caught early in our normalization process, because roll number determines advisor, and so it is actually a partial dependency here, and this would not have come to a situation where we have to analyze for multi-valued dependencies. Okay. So, here is a formal definition for multi-valued dependencies. So, consider the relation scheme R x y z. So, the MVD x multi-determines y holds on R is said to hold on R if for any instance of R, any instance for the presence of these two tuples like having xxx y1 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 z like this, that means these two values are same. Okay. So, these two are not necessarily the same. Okay. If the presence of these two tuples guarantees the presence of the other tuples, where how do you obtain these tuples? We basically swap the values of these two tuples, these two values here. So, take out this y1 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 and then put it here. So, you will get xxx y1 y1 z z2 z2, right. And in a similar way you take out this value and put it here, you get this. So, swap the two. If the presence of these two tuples always guarantees the presence of these other two tuples, then we say that MBD x determines y holds on that relation. And by there is a symmetry in this definition, and so if x determines y holds, then actually x determines x multi-determines z also holds actually. Now, notice one more thing here, that supposing there is a FD, okay. In fact, every FD functional dependency can in fact be thought of as a multi-valued dependency. So, I am claiming that the multi-valued dependencies actually generalizes the notion of functional dependencies. Supposing there was actually just a normal FD functional dependency x determines y. If x determines y actually holds, then if you have two values here, these two values should have been actually same, right. So, it will be like this also will be y1 y1 y1, okay, and the swapping of these two will result in the same tuples anyway, okay. So, the definition kind of holds even though if you think of it as FD. So, MBDs actually further generalize the notion of functional dependencies. So, in functional dependency on the right hand side you had a single value, but now you have actually in some sense a set of values. Okay. So, that is the definition. Now, here is an alternate definition of the multi-valued dependencies in terms of joins. Okay. So, let us say again consider some relation like this x, y, z, and let us suppose that x multi-determines y, then by symmetry we know that x multi-determines z. Now, you can actually say that the x multi-determines y exists in terms of this decompositions actually, okay. So, if you consider this decomposition x y x z of R, okay. So, we can now say that x multi-determines y if for any instance R is actually equal to the projection of the original relation onto xy, natural join with projection of the relation onto xz will be equal to R, right. So, if you do a projection here, for example, in the roll number, course number, friend email address, that example, if you do a projection here on roll number and course number, you will get for every student all the courses he or she is doing, and here you will get for every student all the friends he or she has, right, and the key here will be xz and the key here will be xy. Now, do a natural join, the only common attribute is roll number, and so every course should get combined with every friend, and you will get, if you have half a dozen courses and 10 friends, you will get 60 tuples, right. So, that is what we are saying. So, that is what the definition also said, and we are putting it in another way here, saying that if you project the relation onto x y and x z, do a natural join, it should be equal to R. So, here is an alternate way of defining the existence of a multivalued dependency. Okay. So, now we are ready to define the fourth number form. So, before that we will also define when you call MVD as a trivial MVD. An MVD X multi-determines Y on scheme R is called trivial if Y, the right hand side, is a subset of the left hand side, or the union of these X and Y is actually equal to whole of R, otherwise it is called non-trivial. Now, for fourth normal form, you remember look at this, the numbering. First normal form is already there in the relation definition itself. Second normal form we defined, third normal form we have defined, and where we gave concession for prime attributes, and then naturally BCNF should have been called fourth normal form if we are actually following the sequence number. But then actually fourth normal form is defined in terms of multivalued dependencies, and then later we discovered that we need something stricter than third normal form, which is possible, and so Boyce-Codd normal form came in between in some sense. So that is why the numbering is different. Okay. So, fourth normal form, a relation scheme is in fourth normal form if it is in Boyce-Codd normal form, and for every non-trivial MVD now X multi-determines A, X must be a super key of R. Okay, X must be super key of R. Now, this student course that friend email address, that relation is not in fourth normal form, because roll number multi-determines course and roll number is not a super key. The key is in the entire three set, the set of all the three attributes together is the key. So, roll number is not a super key, and this is a the union of these two things is not the entire relation, and so it is a non-trivial MVD, and so this does not satisfy our definition that the left hand side should be super key. So, what we now suggest of course is to decompose this into roll number, course number, and then roll number. Of course, what I am trying to say here is interesting. Given to you, left to ourselves, we will never naturally design this kind of a relation. But if this relation came into the picture inadvertently into your design, then the machinery up to using functional dependencies cannot detect any problem with this. That is why there is a theoretical need for having a multi-valued dependency, and so we define that and then say that such kind of things are not in are not satisfying fourth normal form, and they should be decomposed.
Okay, so let us move on. We have considered fourth normal form and multivalued dependencies and fourth normal form so far. Now, a natural question that comes up as a follow up of the definition of the fourth normal form is that recall that fourth normal form was defined saying that something is a is equal to the natural join of two relations. Okay. So, now naturally that a question that comes up is why 2, why not more? Okay. So, it is in this context we define what is called the joint dependency or it and the corresponding normal form called the fifth normal form. Okay. So, joint dependency is defined like this. This is a generalization of the multivalued dependency, and it is called written like this JD R1 R2 RK, where R1 R2 RK are all individual schemes. So, a JD R1 JD R1 R2 Rk is said to hold on some scheme R if for every instance of that particular relation R, where R this instance R is on the schema capital R, which is union of all this R1 to R1 R2 Rk. Okay. So, for every instance of R, if it so happens that if you project R onto R1 R2 Rk, okay, and then do a multi-way natural join, you get back your R. Okay. So, it is written as R is equal to multi-way join of pi R1 R, pi R2 R, etcetera, pi Rk R, and please read this R1 as R subscript 1. It is the same as R subscript 1 and R subscript 2 like that. Okay. So, this kind of a condition is indeed very difficult in practice to know, to kind of find out that it is occurring in the data. So, in some rare situations this kind of a condition might hold, and in such situations we will define the normal form. So, a relation scheme is said to be in the fifth normal form with respect to a set of functional dependencies, multi-valued dependencies and joint dependencies. Okay. If it is already in fourth normal form, and for every non-trivial JD, okay, JD R1 R2 Rk, each of these Ri's is a super key. Okay. So, that is how we define the fifth normal form. Fifth normal form with respect to a bunch of functional dependencies, MVDs and JDs. If the relation scheme is already in fourth normal form, and for every non-trivial JD, Ri is a super key. Now, let me give you an example. So, consider this particular example situation. So, we have a relation called student project skill with three attributes: roll number, skill and project, and then three relations called student skill with roll number and skill, which basically records as to who has what skill, and then student project indicating that who is interested in what project. So, roll number and some project ID kind of thing. And then finally, one more thing, we have skill project, which basically records that what project requires what kind of a skill, right. Now, these are the three individual relations that result from, actually that can be considered within this context. Now, let us say there is a particular rule or situation that prevails, which says something like this, that if a student R1 has a skill S1 and the student R1 is indeed interested in project P1 and project requires the skill S1, then it should be the case that R1 S1 P1 must appear in our student project skill relation. Okay. So, this is the prevailing condition there. So, in such situation we will you can actually see that the student project skill relation is the multi-way natural join of these projections called student skill, student project and skill project. Okay. So, in such situations we say that this joint dependency holds. Now, if you look at the actual data, like for example, this roll number skill, roll number project and project skill individual relations. Let us say there are some R number of students and P number of projects and S number of distinct skills. Okay. And we will also notice that in this particular 3 column table, there are actually no multi-valued dependencies. There are no multi-valued dependencies. Okay. Now, if you focus on this, the maximum size of this can be at most R times S. Okay. So, every student may not have every skill. So, in typically it might be much smaller than R times S, but the maximum is R s. In a similar way, every student may not be interested in every project, and so this will be less. And similarly, all projects need not require all skills. So, project skill table will be having some size that is less than S times P. But then if you focus on this, for appropriate numbers of this chosen appropriately or PS, you can see that the size is upper bounded by RPS, but then RPS is typically much larger compared to RP plus SP plus RS. And so, and because of this requirement that if a student has a particular skill and is interested in a particular project and that project requires that skill, then that combination must exist here, R1 P1 S1 must exist here. That is the data, that is the condition that under which we are operating. Then it is highly likely that this will have a huge number of redundant tuples. Okay. So, there is a huge amount of data redundancy here, and so we will say that the joint dependency exists here, and we are we are advised to avoid this kind of design. Okay. Okay. So, these joint dependencies are very difficult to detect in practice, it might actually not occur. So, most of the time we will focus on obtaining designs that are into fourth normal form. Okay. Now, moving on to kind of close this module on discussion about normal forms, we consider two kind of approaches for the overall relational database design. These approaches are bottom up design and top down design. So, let us see what they are. So, and the theory that we have discussed is actually applicable for both these kind of situations. So, the bottom up approach is what is called also called as a synthesis approach. So, in the synthesis approach, what we do is we identify all the attributes of interest in the domain that we are modeling or in the database that we are modeling, and keep all these attributes in a big universal relation. And then by doing a careful study of the domain, we have to determine all the functional dependencies, all the multi-valued dependencies, and if possible, if there are JDs etc., all of them we need to determine and write down. Then we can use the algorithms that are discussed in this particular module in order to decompose this universal relation into those individual relations that satisfy this highest normal form, maybe fourth normal form etc., and then actually obtain a relational database design. Okay. But the downside of this approach is that it is kind of very difficult to obtain all the functional dependencies in a very large database with hundreds of attributes. Okay. And the specific, and as you have noticed while we were discussing the algorithms are actually non-deterministic. So, that means there are certain choices in the algorithms which which can be done in multiple ways, and so may result in multiple designs. So, this approach is not really that popular in practice. So, in practice what we use is what is called the top down approach or the analysis approach, where we basically do a modeling based on certain conceptual level data models, like the entity relationship model that we have discussed in our course, and then generate a relational database design by representing these entities and relationships as individual relations, which basically group these attributes that are belonging naturally to each other. And then on those smaller relations, we determine the functional dependencies MVDs that are applicable among those attributes, and then carry out an analysis of these relations individually and also sometimes collectively to kind of to ensure that they are meeting the normal forms requirements, and if necessary we will do we will carry out decomposition to obtain desirable properties. So, this approach is much more popular, and these of course, the theoretical observations that we made about the normal forms and then the dependencies that exist and things like that, they are kind of applicable in both approaches. It all depends on how actually we make use of them in practice. Okay. So, with these observations, let us now close this particular module, which is module on relational design normal forms. Okay. Thank you.